So you have two masses suspended from a string, one on a large cylinder, one on a small cylinder. You're given the radius of the large, the radius of the small. You're given the mass of one of the hanging weights, and we're told these are at equilibrium. So the torque, the sum of the torques equals 0. That's how this person approached it. Fine. I like to say that the torque going in one direction equals the torque going the other direction. M times G is the weight, it's the force. This person chose to leave the weighted, fine. The G in there, it's fine. So now it's a math problem. Anybody not see how that was done? Any follow-up questions on that? Looks good to me. All good. So I guess this is actually, this person used 9.8. What is that? Yeah. 98. No, what did they get this? Yeah. 9.8 times 0.5 times 20. Yeah. 98. Any questions on that, girls? It's a very straightforward, weight, moment arm, weight, moment arm. So, okay. This one here, two identical forces act at a distance 3 meters from a pivot point. One acts at an angle of 180, 120. The other acts at an angle of 60 with the same force, same moment arm, just different angles. So whoever did this proved that these two torques are equal because if you know your trig, the sign of complements, and this is good job. It's actually, I think it's called, no, not complements, supplementary angles. Yeah, complements when they add up to 90. So 120 and 60, they add up to 180, and that's always true. That sine of 120 equals the sine of 60, or the sine of 10 equals the sine of 170, and the sine of 20 equals the sine of 160, which is, 120 equals 60. So I'm going to amplify what I just said with a picture because I'm trying to help you for the test. Here are two identical forces with an identical moment arm, the same distance from the pivot. These two torques are exactly equal because, well, you can say that this torque is this huge angle. It's one way to look at it. Or you could say that you're allowed to use this little angle because actually they would give the same torque anyway. These two forces apply the same torque, assuming they're the same force with the same moment arm. Even though they're different angles, they're identical torques because they're supplements. Is that what it's been a long time. Is that what you call it? Supplements when they add up to 180? Is that right? It's been a long time for me. Supplementary angles, is that the correct term that this person used?
Yes.
Okay, good. So I'll just say they add up to 180. So remember that. So I'll show you again. Same force, same applied at the same point. They are supplements to each other. They have the same. These would provide the same torque. So remember that for the test. Let's go back to here. So good on that one, girls. Problem 2. I don't mind going over it again. 120, 60, or 110 and 70, or 180. Angles, supplementary angles have the same torque because the signs are equal. This person showed this really well. Here's a rod and it has a pivot point here. And the rod has a mass called M, I think. Yeah, the rod is a length L. It should be a little L, I guess. And it's supported by a thread. Determine the magnitude and direction of the force exerted on the rod by the axis. Well, this really is nice and simple because this axis, this only exerts one force, and that's vertical. So, well, if I could find this is an up force, this is an up force, and this is a down force. So actually, if I could find the force of this thread, I'll have the up force and the down force, and I can know the sums of the ups equal the sums of the downs. So I have to do as a torque problem. How do I find the thread? The tension of the thread we'll call T. And let's be consistent. They called it little l. We'll call it little l as well. So we'll change this to little l. So the torque of the thread is what? Well, its moment arm is L, its force is T, because we don't know what it is, and it's at 90 degrees, so I don't need trig. So this torque over this way equals the torque, the other torque going down, which is mg, capital M times G, times L over 2, because remember, we put the weight for in a uniform beam, or all our rods will be uniform. You put the weight force in the middle. So that's why I did L over 2. So when you, let's see, cross out the L's, because they're on both sides, and you can, let's see what happened here. Yeah, when you cross out the L, it becomes the torque is, sorry, the tension is mg over 2. That's not our answer but now we can find our answer by taking the sum of the y's equals 0. So the up forces, which is the T, and the force we want to find, which is the force of the rod on the bar. It has to be an upward force because that's the only thing preventing the bar from falling. Its weight force wants it to go down, but it's countered by the up force. So the two up forces, the force we want to find, maybe we'll bold it because that's the force we want to find. The tension that we now know, which is we found is mg over 2, equals the one down, which is mg, and I add, I guess I have to subtract mg over 2 from both sides, and the unknown force is F. Well, good girls. Anybody want me to do it again? Just go over it again. Who's that? Just speak, because rather than me going back to the screen.
Can you
Whoever,
just like re-explain the bottom part? Like I don't get like why you're bringing the 2 from up top down to the bottom.
the bottom part, like this second stage
Yeah.
in the forces. Well, because once I get this tension, that's actually not what I'm looking for. We're actually
Then
looking,
you're just substituting.
yeah,
Okay.
I get my T as mg over 2. So my tension I found from above, my up's equal to down. So I just replace this tension that I found up here into mg over 2. And then I subtract mg over 2 from both sides, and I get mg over 2 is the force of the little pivot. Go ahead, just say what you want to say, rather than me have to jump over there. Just feel free to like turn on your speaker and say something. Or did someone just try to come in? Who had a question?
No, Mr. and Ms. Caffrey, can you just make it a torque question by putting a pivot at the like one of the side? That's what I did. I put the
Did it work? Let
pivot.
me check it out. And know that for any AP question, there's always several ways of doing it. Let's see. I'd be curious to see what you did. Let me get to this question. What did you do? Tell me again.
I put like a pivot at the horizontal axis, and then I did
Did
the
we are like right here at the thread
no on the other side.
over here?
Yeah, and then I found F times L equals mg times L over 2.
Yeah, that's what that. F, say it
I
again.
Yeah, it's basically that. I just found like the force. I didn't find any tension.
Oh, well, I was calling that T. I was calling this force the You know what? Actually, you know what I realized? What did you do again? Say it again. Well, I'm calling the T the thread's force. That's what I'm calling T, and I'm calling F the little rod over here. It's upward force. Say it again slowly. What you did? Say it again.
Wait, I think I just read the question wrong.
Oh, okay. So there you go. And anybody else need another trip around this one? You good?
I think I understand what Julia was saying. Like, if
Let me
you
hear it.
put a pivot point for the tension, then that gets rid of it. And if you do a torque, it would just be like F times L equals mg times L over 2, and you're still going to get F equals mg over 2.
So where are you putting the pivot point again? Say that again.
Where the thread is, because
Oh,
then
okay.
that eliminates it.
Yeah. So you got this. You got a downward. Yeah, that's a better way to do it. That's really good. Put pivot point here. Then mg equals this. Actually, I pulled a solution from another source. That's a way better way to do it. Put the pivot here. It's mg mg times L over 2 equals, is that what you, yeah, F times L. Well, I guess that's really the same thing, right? It works. If it works out, works out. Totally good. I think you get the same thing. Yeah, you get the same thing. So that's fine. That's good. You get to put the pivot point where you want to put it. If it works, great. Great, great, great. Okay, everybody good on that one before we leave it? So it's a combination of first a torque, which is pretty typical, and then in F net in the y direction equals 0, substitute the t that you got into this equation. Right over here, see the t gets a substituted, and then you subtract mg over 2 from both sides. I think the next part's a little tougher. If the breaking strength of the thread is 2 mg, determine the maximum distance r measured from the hinge axis, which is over here, that a box of 4m can be placed. So the box, what would it do? It would create a torque this direction, right? It would create a torque in the same direction as the mg, the weight of the rod. So let's see the solution. The thread torque, using the left side as the pivot, the thread torque would be like an up torque, a counterclockwise torque, and the two clockwise torques would be the box that you're placing and the rod torque. Let's see if that's right. So the thread is up. I pulled a solution from another source, but I'm not so sure. Let me work this out. Give me a little time.
Mr. Capri, it says that the breaking strength of the thread is 2 mg.
Oh, okay. Thank you. I just didn't thank you. Got it. So the breaking, that's why this is, yeah, sorry. Thank you. Terrific. It's 2 mg. I didn't read it over here. Thank you. Good. So that does make sense. The breaking torque of the thread is 2 mg. Thank you. So the thread torque equals perfect. And then what did they do? This is just the math after this. What did they do? Move m from every part of the equation. M and g, right? Beautiful. And there's the solution. You just put the L on the other side. And there you go, girls. Any question? Well, anybody want me to go over that again now that I've kind of figured out what was going on here? Just let me know if anybody wanted me to repeat this.
Can you just explain like where they got the part for the rod?
Okay, so here's how it goes. They're using this as the pivot, and they're saying the breaking strength of this, the strength of this thread will break at 2 mg. So you have a torque going this way, and then you have a torque going down. They placed it in the middle because remember we always place the weight of the rod in the middle at L over 2. See, we put the weight of this is the rod. We placed it at L over 2 from the halfway point from the pivot. And then the box, where's that? I don't know. That's just the distance R, which we want to find. We're told the box is 4 mg. It's going to create a torque that's with the rod, and it's going to be counted by the thread. And so this is the state of equilibrium. And so you just remove the mg, and then you solve for the equation. Did that answer your question? They put the weight of the rod in the middle like we always do. Okay. Is that clear now? Did I answer your question? They put the weight.
Yeah, thank you.
Yeah, the mass of really this should be the weight of the rod, right? Weight of rod, and this should be the box torque, right?
Could you re-explain it, like how you got the equation?
Sure. So what we do is you want to place a box somewhere here, and you've got this thread that's got a limit. It can only take so much. So you just can't place the box anywhere. So you say, well, look, let's take it to the extreme where there's just equilibrium, and if I just shift it over a little bit more, we get breakage. Maybe if it's equilibrium here, if I shift it over just to the right, this thing's going to break. So let's look at the torques we have. We have the rod's torque and the box's torque that are using this as a pivot that'll be counted by the thread torque. And so that's what we have. Thread torque. We're going to set where they equal thread torque at equilibrium will equal the box torque. Now I don't know where to place the box, so they just called it R. You can call it X if you'd like. So the thread torque will be equal to the box torque and the rod torque. So you're going to place it. So now you just cross out your MGs. You get 2L equals 4R plus L over 2. Get the L's on the other side. Use, subtract and get the L's on the other side. So if you place it at 3/8 L, right about here, that's going to be the point where if you just slide it over a little more and give it a little bit bigger torque, this thing's just going to break. Okay, so that is it. Everybody good now? I want you to never feel like you can't even ask me to do it again. Just let me know. So now, here's another way it was worked. Here's, I think this looks like Kim's work here, if you want to look at it. She says the sum of the torques. Well, you can see it worked out. I think it's really no different than what that we just did. And now here's a classic weight on a rod supported by a diagonal thread, horizontal uniform rod. You're given the length. Everything's labeled nicely. On the diagram, draw all the forces and label the vectors to represent all the forces acting on the rod. So what are they? Well, obviously there's 1 force, 2 force. The weight, I think, does the rod have a weight? Yes, it does. Here's the weight of the rod. And then the last force is the hinge will exert a force up and to the right. Why to the right? Because if the tension's going to the left, there's something that has to counter the tension, because the sum of the forces in the horizontal direction equals 0. Now, also the rod doesn't fall, so it must be supported up as well, up and to the right. I really can't write on this because it's a Google Doc and I don't think I can write on it. So I'll say it again. There's the tension, 1, the weight, 2, the rod, 3, and the hinge that's up and to the right. Okay, calculate the reading on the spring scale. Well, the person who did this recognized the sum of the torques equals 0. She placed her pivot on the right to eliminate those 2 unknown forces. And what torques did she have? She said you got a torque this way, 1 and 2, and they are balanced by the torque of the spring. This would be a counterclockwise torque, a clockwise torque, a clockwise torque. Let's see what she did. So she's got the 20 newtons at 0.3. So the weight of the rod she placed in the middle, this is 0.6. She placed the weight 2 times 10. She placed it in the middle, which is good. What's the other torque? Well, the weight at the end, that's 0.6. It's did she do that right? Let's see. Yep, 0.5 times 10 is 5. And what it countered those 2 torques? Well, the diagonal spring scale, its force, it's at 0.6 meters away from her pivot. She used T sine theta. Sine of 30 is 0.5. 0.5 times 0.6 is 0.3. So 6 plus 3 is 9. Divide both sides by 0.3, and you have T. Let me know if anybody wants me to do it again. I have no problem. Maybe slower. Let me know. Okay. Nobody needs me to do it again. I'm going to eliminate that because there's nothing like that on the test, the hinge question. Problem 5. Let's take a look. We've got a classic weight on a rod. Let's see. This is actually what you did for homework. I just put it here again. Let's see the work she did. So clockwise torques equal the counterclockwise torque. She used the end of the rod as a pivot. So she's got the counterclockwise torque, T sine theta D. She put the weight, well, the weight is in the middle, isn't it? 400 times D over 2. So that became, I guess, yeah, the 400. What happened here? Oh, she has the moment arm of 2. Is this rod? How long is this rod? Let's see. Actually, oh yeah, she just called the rod D. I get it. So D over 2. What happened? What did she do here? Let's see. 400 times D over. Why is she canceling? I don't know what's going on here. Is this you, Kim? Did you do this?
Yeah. What are you confused?
These canceling out of the. Where are you getting these 2s canceling out?
Oh, just because I put the weight force, which is mg, I multiplied it by the d and then put that over 2 and then just canceled out the 2's to make it cleaner so that way there was no denominator.
Oh, you multiple. Oh, I'm sorry. You multiply both sides by 2. Got it.
Yeah.
I get it. Multiple. She cleared the fraction. Totally got it. And looks like some good work. And she moved the D's from both sides. And I get it. Very good. Is that clear to you, girls? She did it. She has 2 torques. She sees the 2 torques. This torque is countered by that torque. And she, there you go. Very
Mr.
good.
Manjicapri,
Yeah.
how do you know what to make counterclockwise or clockwise? Or like, do you
Well,
just, yeah.
look at this tension. What this is your pivot. This a force in this direction would cause, if it was free to rotate, if it didn't have a counter torque, this would cause this would it's tugging in this direction, so it would cause a rotation like this, a counterclockwise. Whereas this would cause, if it were not counted, like if I just took a scissor and cut this would cause a rotation in the clockwise direction. See? So just imagine that we're
Thank
free
you.
if it weren't counted. And this, if it were not counted, would cause a rotation this direction. All right, let's see. Then she does the second half, which is pretty typical. That's just the first quarter problem where she says the sum of the forces in the y direction is 0. Let's see, what are we solving for? B, what are the vertical and horizontal components that the wall exerts on the beam? I really don't have a question like this, but it's, she did the sum. She said all the up forces equal to down forces. And what did she have? She said the vertical component of the T is an up force, and the walls, she called the walls force F, so it's an up force as well. The wall would exert an up force and prevent the beam from falling. So this up force in T sine theta equals the only down force, which is 400, and she works it through as 200. And then she does the sum of the forces in the x direction equals 0. What are the x's? Well, it's the horizontal component of the T. That's an x going this way. And the wall counters that to make the sum of the forces in the x direction be 0. And so what does she do? Fx, the wall's x force, equals T cosine 40. And she works it out to that solution. So there you go. There you go, girls. Anything else you want to just sort of a last minute? Let's see, what time is it now? 8:30. We're about at the end. Who's waving? Who's raising the hand? Angela, what's up?